Okay, this is for our Unit 5, Lesson 2. It's over graphing polynomial functions. Now, we've talked about a polynomial. Poly means many, and so we have many terms in a function, and our exponent can really just be anything. We've dealt with quadratics in the past where our highest exponent was x squared, and we worked our way down to an x and then a constant, and that always makes a parabola. But now we're dealing with a lot of different shapes, and we're going to introduce them in this lesson. So it says up here, a polynomial function is a function of the form f of x is equal to, this is read, a sub n to the x to the n power plus a sub n minus 1 x to the n minus 1 power, and we keep working our way down until here it says a sub 2 to the x squared power plus a sub 1 x plus a sub 0. All this means is we have a polynomial. It could have many terms. We have x, this a sub n to the x to the n power is just saying our highest power of exponent, okay, the largest number in the exponent should be first. And then this next term, how it says n minus 1, it's the next highest, it's 1 less. And then n minus 2 means it's 2 less than the first. And we keep working our way down until we have our x squared, our x, and then a sub 0 would be our constant. So that's standard form, and we introduced standard form in lesson 1 of this unit. It says that we're not going to be using any negative exponents for right now. Okay, a sub n is called the leading coefficient. And a leading coefficient is the number that's in front of the variable or letter that has the largest exponent of the whole polynomial. So we'll kind of practice in this next part, identifying what the degree of a polynomial is and the leading coefficient. So we're going to start small and work our way up. So our first function is f of x equals 4. If you notice in this function, it does not have an x or any variable in it. So 4, this is what we call a constant, okay? No variables. So when we have just a constant, which again is just a number, it's a degree of 0. The degree is, again, the highest exponent in the polynomial, and if we do not have a variable, we don't have a highest exponent because it has to be attached to that variable. So the leading coefficient, though, in this would still be 4. It's the number, the only number in the problem. In our next problem, we have f of x equals negative 5x plus 1. So the degree comes, again, from the variable with the highest exponent. The only variable in this problem is x. The x is not explicitly showing us an exponent at this time, but remember, if it's not showing it, there's an implied 1. So anytime 1 is the highest power, we have a degree of 1. And again, that would be also called linear, but the degree is 1. And the leading coefficient comes from the variable that's in front of that x. So the leading coefficient would be negative 5. Okay, let's move on. We have f of x equals 12x squared minus 11x plus 31. The highest powered variable here is my x squared. So we would call this a degree of 2 because that 2 right here is the highest power in the whole problem. And the leading coefficient, again, comes from the number in front of that x squared that told us the degree. So the leading coefficient is 12. Okay, if we have f of x equals negative x cubed minus x squared plus 8x plus 1, the degree will come from the highest exponent, which is 3. It's cubic. Maybe I should put all these in here. 3 means cubic, 2 is quadratic, 1 is linear. Okay, so if we have this x cubed, the leading coefficient comes from the coefficient. We just have a negative sign. Remember, that's the same thing as negative 1. So negative 1 would be our leading coefficient. Okay, moving on. Our next problem is negative 3x to the 4th plus x squared minus 18. My highest power is 4. So this is a degree 4, which is called quartic. Kind of a funny word. And the coefficient of our x to the 4th power is negative 3. So that's my leading coefficient. And my last problem, We have 9x to the 5th power plus 2x to the 4th minus x cubed plus 9x squared minus 2. Again, the highest power is 5, so it's a degree 5, which is called quintic. And the leading coefficient is the number in front of that, so that would be 9. Now, each of these types of functions with their different degrees make a different type of line when graphed. So we're going to go over the parent function, which gives a general shape of each type of degreed function or polynomial. And remember, the parent function is just like the basic setup for each type of function. We can have transformations that are made to each of these parent functions. It can be shifted up, down, left, right. It can be stretched. It can be shrunk. It can have lots of things reflected. It can have lots of different things happening to it, but the parent function is how it originates in its most basic form. So starting off, our constant function right here, this would be if we had f of x or y was equal to our constant, which is just a number. When we are equal to just a constant, we have some type of horizontal line. It has zero slope, it's flat. Okay, so again, that could be shifted up and down all over the place here on this grid, but when we're equal to a constant, it is a horizontal line. Okay, next, we have linear, and we're really familiar with linear. In pre-algebra and algebra 1, you spend a lot of time with linear functions. This would be if f of x was equal to just some kind of x. Okay, there's no exponent attached, and you can have numbers added to the front of x or after x, but what that makes is a diagonal line with a positive slope of 1 over 1, and it passes through the origin. So that's a linear function, a diagonal line. Okay, the next, we're very familiar with quadratics by now. We know that a quadratic is when our x is squared. So we say the parent function is f of x equals x squared. And a quadratic, again, we should remember this, we spent 2 whole units on it, is a parabola. And the parent function passes through the origin and is going up like that, like a big smile. Okay, so that's a quadratic. Now cubic, this is one that's a little bit new to us. A cubic is when we would say f of x was equal to x cubed, that's our parent function, and our arrows end in opposite directions. We start down and we kind of curve and we go through the origin and then we turn back up. And that's a cubic function. Okay, the arrows end in opposite directions. That's a big deal, and we'll talk more about that later. And then we have quartic. This is power of or degree of 4. So we would say f of x is equal to x to the 4th power. When we have it to the 4th power, this is very similar to a parabola. Okay, we have this even exponent, and it goes through the origin, and arrows are both ending up for this parent function. Now we'll learn as we move on and graph different types of quartic polynomial functions. There can be different stuff happening in the middle, some bumps in there, but this would be an example of just the parent function. And then the last one that we will learn and talk about in algebra 2 is f of x is equal to x to the 5th power, and this is quintic. Again, it has an odd degree, so it's actually very similar to our x cubed. It's going to end with arrows in opposite directions. It's coming from down, and it turns to go up, passing through the origin. And again, you'll learn it can have some more up and down bumps in the middle, some turning points we will call them. But if we don't have any other terms, this is what it would look like. So you'll notice a trend. If we have an even exponent, we get kind of parabolic in shape with arrows ending in the same direction, up or down. And if we have odd degreed functions, our arrows end in opposite directions. And that's going to help us identify some end behavior, and that'll be our next part. Okay, in this next section, we're going to talk about end behavior. Now, end behavior, we've talked about this a little bit a couple units ago. End behavior is, are we ending up or down on each side, basically, of this graph? On the right side, which is x approaching positive infinity, are we ending up or down for f of x, which is y? And on the left side, as x approaches negative infinity, are we ending up or down? Positive or negative infinity are the answers we are selecting here. Now it says, using your graphing calculator, determine the end behavior of the following functions. Now, I'm even at home. I didn't bring a graphing calculator home with me, but I have the Desmos app. So I recommend if you are working things from home, get the Desmos app on your smartphone or go to desmos.com. Okay, that is Desmos, Desmos. Okay, it's an app or it's a website. But I threw this in, just typed in the equation, 4x to the 4th power plus 6x cubed minus x. And let's see if this is my x and my y axis. Okay, and I throw this on, I get roughly something that looks like this. Okay, this is the picture that I'm shown on the graphing app of my equation, 4x to the 4th plus 6x cubed minus x. Now remember, if we have the x-axis, that's the left and right, as we move to the right, x is approaching positive infinity as the numbers are getting bigger and bigger and bigger until we get to infinity. The left side is for our x is approaching negative infinity, because as we move left, we're getting more and more negative, which is negative infinity for x. So what we're asking here, as x approaches infinity, when we are on the right side of the graph, which is this side, is f of x, which is y, is it ending up or down? So notice our arrow is ending up, and up for y is positive infinity. So that's all we have to put because it's ending up, positive infinity. Now it says as x approaches negative infinity, which we now know is the left side, is f of x, or our y value, it's the same thing, is it ending up or down? Well, it's ending up. Again, up is positive infinity for y. And it makes sense that we have the same answer, infinity, for both, because both arrows are ending the same direction, up. So that's it, piece of cake. Okay, on number 2, we are answering end behavior for the function f of x equals negative x squared plus x. So if I type that in to my graphing calculator, here's my x and y axis, label it, and the picture that I'm getting is what I would call a sad parabola. Okay, so it looks something like this. So let's remember again, I'll label when we are on the right side for x, that's positive infinity. When we are on the left side, we are at negative infinity. So let's answer our end behavior. As x approaches infinity, again, that's the right side. F of x is ending what? So we're on the right side. Obviously, this arrow is ending down, which we call negative infinity. So we're going to put negative infinity is what f of x, or y value, is approaching. As we keep moving to the right, we are going to keep going further and further down, in other words. Our next part, as x approaches negative infinity, ooh, kind of zoomed out there. That would be the left side. We would say, again, when we're on the left side, which is negative infinity, we are also ending down. Down is negative infinity for y. So f of x is also approaching negative infinity. Again, matching answers on this one because both arrows were ending in the same direction. They're both ending down. Okay, number 3, we have f of x equals 2x cubed. So let me show you a sketch of that. If we put it in, here's my x-axis, my y-axis. My right side is positive infinity. My left side is negative infinity. If I type in 2x cubed, okay, cubic functions, it kind of looks something like this. So if you notice ahead of time, my arrows aren't ending the same direction. They're going in opposite directions. So I'm going to have different answers here. So as x approaches infinity, when we are on the right side, this is my right side, my infinity side, we are ending up. Again, up is always positive infinity for our f of x, or the y value. F of x and y are the same thing for these purposes. Okay, our next part, as x approaches negative infinity, when we are on the left side, we are ending opposite of that. We're ending down. Down is negative infinity for y. So we would say f of x equals negative infinity. Again, I have positive infinity for one answer, negative infinity for the other, and that makes sense because they are ending in opposite directions. Okay, number 4, we have f of x equals negative x cubed. So let's sketch this. My x, my y, right side is infinity, left side is negative infinity. When we sketch this, negative x cubed kind of is a flip of what we had before. We start high and we end low. Something like this. Okay, so let's answer. As x approaches infinity, again, as we are on our right side, this is the right side or the infinity side for x, notice we are ending down, so that we are approaching negative infinity for our y value. Okay, and then as x approaches negative infinity, that's our left side. Okay, so my left side, my graph's up here. We're ending up, which is positive infinity for y. And opposite answers because we end in opposite directions. All right, on number 5, we have f of x is equal to negative 2x squared plus 4x minus 7. So typing that in and getting a quick sketch. Here's our x and our y. Positive infinity is on the right, negative infinity is on the left. And in my sketch, see negative 2x squared, we have something that looks like this. Again, that's a very rough sketch, but that's okay. We just need to answer end behavior. So for our end behavior, as x approaches infinity, so when we're on the right side, we are ending down. As x approaches negative infinity, the left side, we are also ending down. They're ending the same direction. So we could say f of x, or our y values, are approaching negative infinity, meaning more and more negative the further outwards we spread. Okay, and our last example like this. On number 6, we have f of x equals 1/2 x cubed plus 7. So here's our grid. Now this one looks a little bit like this. Okay, so keep in mind this is my infinity side, this is my negative infinity side. So as x approaches infinity, as I move to the right, okay, so we move outwards to the right, this is going to continue to move upwards. So we are ending at positive infinity for f of x. As x approaches negative infinity, as we move to the left forever, this will keep moving more and more down, which is negative infinity for y. Again, ending in opposite directions, so our answers are opposite for the infinities. Okay, now this brings us to some general rules that we can identify end behavior without graphing just by knowing the degree, if it's even or odd. Like even numbers, remember, are 2, 4, 6, 8, 10. Odd is 1, 3, 5, 7, 9. So based off the highest power or degree, that will tell us certain things, and so will the leading coefficient, whether it's positive or negative. So here we go. Let's start with our even degrees. These are like x squareds, x to the 4th, and so on. Evens always end in the same direction. Okay, so evens end both going up or both going down. If we have a positive leading coefficient, positive to me means like going like up, because positive numbers, the higher up we go, the more and more positive we get. So our end behavior, if we have a positive leading coefficient and an even degree, both of our arrows will end going up. Now we can have some business going on in the middle, some up and down turning points, but when it comes down to how we're ending for our arrows, they will both go up. Now if we have an even degree and a negative leading coefficient, remember negatives in front of like our x squared when we did parabolas meant a reflection, meant going down. And it still means that when our leading coefficient is negative and we have an even degree, both of our arrows will end going down. And we should have noticed that trend like looking at number 5 when we did it, and also number 2. They were both, leading coefficients were negative, like we had an x squared even degree, and they both ended down. Okay, now let's talk about what happens if we have an odd degree. Odds always end opposite, and I like it to remember it that way because it's like our alliteration. They both start with O. So odds always end opposite. Now if we have an odd degree, again this would be like x cubed, x to the 5th, or even x, and we have a positive leading coefficient. Okay, positive leading coefficient means we end going up. So our ending one's going up on the right, but because we have to go opposite, the one on the left side would be down, okay, for its end behavior. So again, that matches up. Positive leading coefficient, odd degree. Now what if we have an odd degree and a negative leading coefficient? Okay, if we are odd degree, x cubed, x to the 5th, and so on, and our number in front is negative, we are ending negative or ending down. And because it's odd, they have to end in opposite directions. The one on the left side would end going up. Okay, now that answers in behavior, which can help us answer what we were doing before, approaching infinity or negative infinity. when we're in certain directions, just by knowing if we have a positive or negative leading coefficient and if our degree is even or odd. And we'll practice that here on numbers 7 and 8. Let's look at these. So it says, in our directions, determine the sign of the leading coefficient and whether the function has an even or odd degree. Well, I'm going to look at this now because my arrows, I noticed both of these arrows are ending in the same direction. I would say, because remember, if they're the same for the direction they're ending, that's an even degree. So let's answer that right away because they're ending the same direction. That's one answer. Now my next answer is, do we have a positive or negative coefficient? Now think about this, since they're both headed down, that's getting more and more negative. So because they're going down, I would say we have a negative leading coefficient. Okay, so that's all we had to answer. And again, I could tell by the way the arrows were ending. Now on number 8, look at where my arrows are doing, and it comes down to how these arrows both end. They end in opposite directions. Because they end in opposite directions, this is an odd degree. Because they end opposite. One's up and one's down. Now, when you have an odd degree, even or positive or negative comes from the one on the right side, this one right here. It's ending up. If we end up, that is like positive numbers, right? So this has a positive leading coefficient. Okay, this next section of our notes is about turning points. So we've learned about end behavior. Now we need to learn about what happens in the middle section of the graph. And our graph can change direction, and that's called our turning points. It kind of makes like a bump, like a hill, or a valley, like a dip. So let's talk about what that looks like and how to identify them. And we'll also talk about increasing and decreasing intervals. So the points at which a polynomial function switches direction is a turning point. Okay? If the turning point is higher than any nearby point, it is called a relative maximum. Now we call it a relative and not like the ultimate minimum or maximum because one of the arrows may be ending up. It's not maybe the true highest point. It's just the highest point that we can kind of calculate for that location or that spot on the graph. If the turning point is lower than any nearby point, okay, the lowest would be a relative minimum. Looks like it's a bad handwriting day for me. Sorry. Maximum and minimum values are called extrema. And I actually don't use that word a ton. Maybe I should, but I won't use it a lot. Turning points define where the function is increasing or decreasing. So increasing means where we have a positive slope. So it's our x values where we have a positive slope. And decreasing is our x values where we have a negative slope. And we'll learn how to identify those. We've done it a little bit back in the end of Unit 3. All right. Now this next section is a little tricky for me because I don't have a way of showing you the graphing calculator on this app that I use to make your videos. If you do have your own graphing calculator, this is what it's talking about, how to calculate maxes and mins with your graphing calculator, because a lot of times the max and mins are at decimal point values, which don't show up on our table of values. So it's talking about this function right here. It's a cubic function and tells you if you type that into your y equals, you can calculate the minimum and the maximum values by following these directions. It says to hit the calc menu, and then we select minimum or maximum. We can make these left bounds and right bounds, and then it calculates it. If you do have a graphing calculator and you are trying to learn these lessons from home, you're gonna have to come in to me so I can help show you how to do it. We will practice it in class, and we will go over how you use your graphing calculators to do all these, but again, I don't have a way of pulling that up on a screen for this video. So I can just, I guess, fill these in but I would just recommend using Desmos if you are at home. And then when it comes time for testing, when you're back at school, I can show you how to to do this with your graphing calculator. But for now, I'm going to skip this section and I'm going to move to number 1, and I will use Desmos to help graph this, and that's what you should use that if you are working from home. All right, on number 1, we are going to graph the function f of x equals negative x cubed plus 3x squared. Again, if you're doing this video, get your phone out and type it into the Desmos app, and it will pop up. And it's really nice because it shows you the picture, and then it has little circles where the intercepts and like minimums and maximum values are at. And if you click on those little dots, it gives you the exact values for all those locations. So if I'm looking at the app, one of my circles is at 0, 0. Another one is at 2, 4. So I'm going to go 2 right and up 1, 2, 3, 4. And another one is at 3, 0 right here. And then I'm just going to make it kind of match as best as I can. I'm coming high. I get to this first dot at 0, 0 and I turn and go up. And I get to that one and I turn and go down. And I pass on through and I keep going down forever. So that's like a rough sketch, but that's what I needed to do. And again, I got that from my Desmos app. Now we're going to go through and we're going to answer all these questions: domain, range, and the rest of it. Now remember, domain is your x's, your left to right spread. As I'm on my left side, I'm moving up, but I'm also moving to the left forever. There's nothing stopping me. I'm also moving to the right forever. It's moving down, but it's also moving right. We have outwards, left to right spread forever and ever, and we say that is a domain of all real numbers. Now my range is my lowest to my highest. Now notice my lowest, we're going down forever. We are also going up forever. And we have some switching points in between, but that's okay. It's still part of our up and down forever movement. So we have a range of all real numbers. Okay, now it wants to know, what is our relative maximum? Your maximum is at kind of like you're just one of your highest points, wherever your highest dots are, and I'm going to show it to you right here in red. We can see that this right here is a turning point that is higher than any other turning point. And again, your maximums and mins happen from turning. Notice on the left we were going up, and then we have our 2, 4 value, and then it turns and starts going down. That's why it's called a turning point, and it made a maximum. And that value was, if we clicked on it, was at 2, 4. X was 2, Y was 4. Okay, we also have a relative minimum. I'll show that in green right here. It's a turning point, has to be. We were going down, we get to 0, 0, and then we start going up. So it made a little valley or a dip. Again, that minimum was at 0, 0. Now this graph is nice because they are coming out to whole numbers. That doesn't normally happen, but we'll appreciate it when it does. Now my end behavior, we just practiced this a lot. Remember, the right side of the graph we call positive infinity, the left side is negative infinity. So we're asking here, as x approaches infinity, when we are on the right side, how are we ending, up or down? We are ending going down. Down is negative infinity for y. So we're going to say f of x approaches negative infinity. As x approaches negative infinity, when we are on the left side, how are we ending? Well, this is my left side. It's ending up, which is positive infinity for y. So we'd say f of x approaches positive infinity. Now, our next part, our increasing and decreasing intervals. Again, we use x values to describe where we have positive and negative slope. We basically divide our graph wherever we have a turning point. So I have a turning point here and a turning point here. So I have 1, 2, 3 sections of line based off where the turning points are. So I'm asking, what is on section 1 here, from left to right, what is my slope? Okay, my slope is whether it's increasing or decreasing. Notice it's going down. Now, what numbers do I put? I use x values only. So from left to right, okay, left is negative infinity to this dot, that x value was 0. We were going down, which is the decreasing part of the answer. So I put negative infinity to 0, comma. Not brackets because it's a turning point. It's kind of both up and down, or neither to say because it's the switching point. Now we switch directions. We start going up, which is increasing. But for which x values or between which points are we going up, you could think. Okay, we start where we last left off between 0 and, not that, I circled the wrong thing. Don't look at that. Sorry. And right here where I divided it, that's where we're going up. But which x value is that? That's an x value of 2. So between 0 and 2, we are going up, which is the increasing. Okay, up means increasing, but between which x values? 0, 2. And then we're kind of in my third section, okay, that I labeled. We switch to going back down. So again, that's decreasing. And for which x values are we going down between? From 2 to the right forever, which is infinity. We are decreasing. Okay, so again, we kind of break it up into sections. Our turning points change the intervals, change us from going up, increasing, to down, decreasing. And we're basically dividing the x-axis into sections, and we say from this x value to this x value, we are up. This x value to this x value, down, and so forth. We'll keep practicing it. All right, number 2, we have f of x equals x to the 4th power plus x cubed minus 4x squared plus 5. Again, I wish I could show you. I am kind of expecting you to be following along and using either a graphing calculator or a Desmos app. Again, Desmos will be more user-friendly if you're doing this from home because you just click on the dots and it gives you your exact values. So I click on one of my dots here. I'm just clicking on all my dots. I get a value, and I'm going to kind of round to 2 decimal places of negative 2.32. So I'm going 2 left and a little bit more, and then I'm at 0. So I'm right here. And then I'm going to keep going down. I have another point at negative 1.83, so almost negative 2, and down negative 3.31. So I'm down 3 and a little bit more. 1, 2, 3, okay, about right here. And then I have another value at negative 1.1 for x, negative 1.1 and 0, okay, right there. And then I keep moving up. I have a point at 0 for x, 5 for y. 1, 2, 3, 4, 5, right here. And then I have one more dot at 1.088 for x, so just a little bit past 1. And at 2.95, so almost at 3. So right here. Now I'm going to connect these points and try to make it match as mostly possible as I can. So I'm coming from being up, and I go down to this point, go up, and down, and turn around and go back up. It's a little messy, but we got this kind of lopsided W. All right, I'm going to pause for a second. I'm going to write in these values so we can use them here in a minute. Okay, this should just pop up for you guys. Hopefully you can see all these coordinates. But let's go through and answer all of our questions. Domain and range. So domain again is your left to right outward spread. You should notice as we are moving up for both of these, they're still moving outwards from left to right forever. And so our domain is all real numbers. And I'll tell you right now, all of them have a domain of all real numbers. There's really nothing stopping them from moving outwards in either direction. Now my range is my lowest y to my highest y. Because both my arrows end going up, I can't have all real numbers. I'm looking for my lowest point, which is right here. And for range, because it's the y values, I use that y value, which is negative 3.31. And I'm thinking, okay, are we going greater or getting less than? Because this is going up, it's everything for y greater than negative 3.31. So we would say our range, I'm going to put this in braces, is all the y's, remember that line means such that y is greater than or equal to negative 3.31, our lowest y value. So we'll have a lowest point, and then we're always going above it. And then we want our relative min and maxes. Min and maxes are x values and y values. So I'm looking for all of these coordinates as I move through the graph. So again, where I had like my number for my range right here, that value, that's a minimum. Okay, it's a lowest point. So I'm going to write it as a coordinate. That was negative 1.84 and negative 3.31. Okay, that point was the lowest. I have another lowest point, which is right here. Okay, it's lower, it's a bottom, okay, vertex almost, if you want to make a comparison to our quadratics. So I'm going to say, and we have 1.09, comma, 2.95. Okay, those are two lowest points. And then we have one relative max. Okay, let's go this point right here. I should have done different colors. In blue, it's higher, okay? It's a high turning point. We change from going up to going down. That's a maximum. And that was at 0.5. Okay, and our end behavior. Okay, hopefully we're getting a little bit better at this as we move throughout the lesson. As x approaches infinity means when we are on the right side, how are we ending, up or down? This is our right side. We are ending up, so that's positive infinity that we are approaching as we move to the right. As x approaches negative infinity means as we move to the left. Okay, so when we're on this left side, as we move to the left, we keep going up and up too, so that is also positive infinity. Okay, now on to our intervals. Okay, we're going to have more sections this time because we have more turning points. So I'm going to kind of, again, break this into sections. Okay, I'm going to do it in black to try to show here. And I like that I marked this up because we'll be using these x values, and I'm going to kind of underline them for each of these increasing and decreasing intervals. Remember, increasing means positive slope, decreasing means negative slope, but between which x values we move from left to right. So in this first section, from left to right, I know this arrow is going up, but that's not positive. From left to right, it's going down. It's decreasing. It's decreasing from negative infinity until this line right here. And that x value is negative 1.83. Sorry that I underlined negative 2.32. That was a 0. Okay, so we would say we are decreasing from negative infinity. That's where we always are coming from. For our first thing that we write down, it's always negative infinity. That's the furthest left we get for the x-axis. Comma, negative 1.83. We are going down. Okay, and then in our next section, from this point to our next min or max, which was at 0.5, we are going up. We are increasing. So we say we are increasing between the x values negative 1.83 to 0. That was the x value for that turning point. Okay, and then from this high point to my next low point, we are decreasing, but we're decreasing from the values of x of 0 to 1.09. Okay, we were going down. So 0, 1.09, we are decreasing. And then we switch and we're going up or increasing forever after that. So we are increasing from the value 1.09 to the right forever, which is positive infinity. So notice we repeat values a lot. We always come from negative infinity. That's the first thing we write down. Positive infinity is the last thing we write down because it's the furthest right we could get. But then like other values, they just kind of keep matching up. The last one I wrote down becomes the first one I write down for my next interval. 0, 0, first then last, last then first, however you want to think. 1.09, 1.09. So we at our turning points, we change from our slopes. And again, we use the x values only. All right, number 3, we have negative x to the 4th power plus 4x squared minus 3x minus 2. Let's graph this thing. And I'm sorry, I know these look messy. It's better in person. Or not, who knows? I think so. Okay, so we have a quartic function. Both the arrows are ending down. We have a high point at negative 1.57. So I'm going left 1.5. Then up to 6.49, which is about 6.5. 1, 2, 3, 4, 5, 6, and a little bit. So I've got a point about right there for a maximum. And then we're going down, and I've got a minimum at 0.409 for x, which is about halfway between 0 and 1, and down about 2.5. 1, 2. Okay, right here we have a minimum. Then it turns and goes back up to at 1.16 for x and negative 1.9, so about -2. And then it turns and goes down again. So I'm just going to make a little sketch of this. Let's see, I have a 0, -2.2. Okay, so I'm going, oops, that was bad. I'm going up, down, up, down. Okay, that's my sketch. Okay, this coordinate is -1.57, comma 6.49. Okay, this one right here is 0.41, comma -2.59. And then we have another point that was a turning point right here, which is 1.16, comma -1.91. So again, I'm just labeling all my turning points because they help us identify some of our answers here. Okay, so my domain and my range. Domain is my left to right spread. Again, it is moving outwards as it heads down. Okay, it is still moving left and right forever. So our domain is still all real numbers. My range is my lowest to my highest. Now, my lowest, it's going down forever. So the lowest is -infinity. The highest is at this point right here. And that, for the range, we always use y values. So that would be 6.49. So for this range, we'll write it like this. All the y's such that y is less than or equal to, and let's say 6.49. Okay. Again, or we could do our other notation. Okay, we would say, maybe we'll see this sometimes on Excel, we would say, again, lowest to highest. So lowest, I would say, is -infinity. So we would use a parenthesis because we can't equal -infinity. And my highest is 6.49. So we use a bracket because we can't equal that number. Okay, relative maxes. Let's look for high points, or like the top bump. So my relative max, okay, I have one right here where I just made a blue dot again. And what is that coordinate? If you're clicking on the dot on your Desmos, it tells you again, and I have it labeled -1.57, comma 6.49. It's a high point, so it's a max. Okay, we're also looking for any other high points. It's right here where I just made it in blue. Okay, that high point was 1.16 for x, -1.91 for y. Okay, relative mins, those are like those little dips or valleys. So I'm going to show that here in green. Okay, that is a low point, a minimum for a turning point. And that value was 0.41 for x and -2.59 for y. All right, end behavior. Okay, we'll label the right side as +infinity, the left side as -infinity. As x approaches infinity, when we are on the right side, where do we end? We're ending down, which is -infinity. On the left, okay, we are also, as x approaches -infinity, is our left side, we are also ending down. So x approaches -infinity as well. Again, they match, and that makes sense because they're both ending in the same direction. Increasing and decreasing intervals. Okay, let's cut this into sections again, but wherever our turning points are. So turning point here, see, that's my first section. I'm going to circle this x value because that's what I'm going to use. I have a turning point here. Okay, this is my middle section. I'm going to circle 0.41 because I'll use that number. And on one more turning point, okay, here, I'm going to use 1.16. 3, 4. I have 4 sections that we need to identify. So in section 1, okay, we're in section 1, which is from -infinity to 1.57 for x. So from left to right, this is going up between those two values. That's increasing. So we say our increasing interval is from -infinity to -1.57. So we're going up between those two x values. Now, in my next section, between my next two lines, from -1.57 to 0.41, we are going down. Okay, that means we are decreasing. So I would say we have a decreasing interval between the x values of negative 1.57 to 0.41. And then in my section 3 here, we're going up for a little bit. Between which x values are we going up or increasing? It will be 0.41 to 1.16. Close it up. And then in section 4 that I have labeled here, from left to right, it's going down. And it's going down between 1.16 to the right forever, which is infinity. So we are decreasing from 1.16 for x, comma, to infinity for x. Okay, so again, it's positive and negative slope between which x values, though. Okay, our last problem for this set of notes, we have 2x cubed minus 4x squared minus x. Let's see, I have a high point here of negative 0.12, so I am just left of 0, 0 a little bit, and I am at 0.5059, so just a little bit above 0, 0 right here. And then it's showing me it goes through 0, 0. And then we have a low point of 1.448, which is about 1.1.5, and then we are down negative 3.7. So 1, 2, 3, it's almost about right here. And then it turns and goes up, and it passes through the x-axis at 2.250. Okay, now I'm going to look at my picture, and I'm going to kind of try to make it all match as best as I can. So we're going up, down, up. Okay, there's my sketch. Cubic function makes sense that my arrows end in opposite directions. They're supposed to. I'm going to go ahead and label my highest and lowest points. We're at negative 0.12, comma 0.06. And then we have a lowest point here at 1.45, comma negative 3.76. All right, domain and range. Okay, we have left to right spread, outward spread forever. So our domain is all real numbers. My range is my lowest to my highest. Well, because this arrow is headed down forever and my other arrow is headed up forever, I'm going down and up forever. I have a range of all real numbers. Anytime we have an odd function, we do have a range of all real numbers because they end in opposite directions. Pretty cool. My maximum, okay, my maximum will be right here. It's the only high point or like top of a hill. So that was at, let's see, that's at negative 0.12, comma 0.06. And we have one minimum or low point, and that's at 1.45, comma negative 3.76. Okay, end behavior as x approaches infinity. When we are on the right side, okay, which is here, we are ending up, so that's positive infinity. As x approaches negative infinity is on the left, okay, we are going down, so that is negative infinity. And my increasing and decreasing interval. So the less turning points you have, the less interval changes you have, which means there's less to do, which is nice. We only have 1, 2, 3 sections here. So in section 1, we are going up from left to right. That's increasing. But for which x values? We say the leftist is negative infinity to the x value of this turning point, which is the first value of that coordinate, which is negative 0.12. So we're going to say we are increasing from negative infinity, comma, negative 0.12. And then we change and we start going down. So we are decreasing, but we're decreasing between the x values of negative 0.12 to 1.45 for x. And then in my third section, we're from left to right going up again, and for which x values? From 1.45 to the right forever, which is infinity. All right, that concludes our lesson. There is an Excel assignment that matches this. You won't necessarily have to graph it yourself, but you do need to understand the concepts behind this lesson, so good luck.